Good afternoon YouTube and welcome to my next worked answer video. Today I am tackling a longer 8-mark NMR question where, as well as NMR information, we've also been given an infrared spectrum to analyse. The whole purpose of this question is for us to work out the structure of compound R, for which they have given us the molecular formula at the start of the question. These can be quite tricky, so what I'm hoping to showcase in this video is how I would approach this question, everything that I would annotate onto figures 1 and 2, and how I will then use everything that I've annotated to put together the structure of compound R. Now, to do this, I'm going to need access to my datasheet because I'm going to need to use table B with the hydrogen NMR chemical shift data in, and I'm also going to need table A, which has my infrared absorption data in it too. So I'll be making reference to the datasheet and I'll show you which areas of the datasheet I've been using to help me to piece together the structure of compound R. So let's get going. Okay, so the first thing that we need to take note of is the molecular formula that we've been given, which is C6H14O. I'm always going to be referring back to that when I'm thinking about what particular bonds I've been able to identify from the infrared spectra, but I'm also going to be going back to that molecular formula when I have a look at the integration values that have been provided on figure 2, and I'll also come back to the molecular formula when I've put together my structure of compound R, just to make sure I have everything that I should have, i.e. 6 carbons, 14 hydrogens and 1 oxygen. Now, having a look at figure 1, which is the infrared spectrum, whenever we're having a look at an infrared spectrum, we should never really be looking at what's going on the right hand side down at the lower wave numbers. I would say anywhere from the very right hand side to about 1400 centimeters to the -1, because that's the fingerprint region, and that's going to be unique for every different type of compound, which is really helpful if we had access to the database to be able to compare fingerprint regions too, but we don't. So what we need to be doing in an exam scenario is looking for the peaks that are going to identify different functional groups, and that's what I've been able to do over here. So the peak that I've highlighted in the pink, I've recognised as an OH alcohol peak because that peak is found within the region of 3,400 centimetres to the -1. And when we go across to our data sheet and have a look at table A, we can see that in the region of 3,400 centimetres to the -1, we've only got 2 options of what that peak can be. It could be an NH bond in an amine, or it could be an OH bond in an alcohol. Now, this is the first time the molecular formula is going to be helpful, because in that molecular formula there are no nitrogen atoms. So we know that this particular peak is not caused by an NH bond in an amine, and it thus has to be caused by the OH bond in our alcohol, which makes sense because we know from the molecular formula that it has to have an oxygen atom in there. Now, as well as deducing the structure of compound R, I have to explain each stage in my deductions. So when it comes to explaining the information obtained from figure 1, I would say that there is a peak that is found between 3,230 and 3,550 centimetres to the -1, and that would thus suggest that there is an OH functional group in compound R. I would always give the full range of the wave numbers as it is written on the datasheet in table A. So that's the first thing that I would do. Then we're going to go on to have a look at figure 2. So figure 2 is showing us the hydrogen NMR spectrum of compound R, and I've annotated everything that I like to annotate on either the NMR spectrum, if that's how we've been provided it, or if you get certain parts of the information in a table, I would still be adding everything that I've annotated here just around the table instead. Now, it tells us down here that the relative integration values for the NMR peaks are shown on figure 2. Now, when it says relative integration values, you can see that we've been given them as 1.6, 0.4, 1.2 and 2.4. They are not whole numbers. We can't have 1.6 hydrogens in a particular environment. So we need to turn this into a whole number ratio. So what I did was I recognised that all of these numbers, or rather the bigger three numbers, are multiples of 0.4. So I worked out how many 0.4s went into each of the bigger numbers. So 4 for the 1.6, and then obviously 1 in itself as 0.4, and then 3 into 1.2 and 6 into 2.4. And that is my whole number integration values. Now if I add up the 1 hydrogen in that environment, the 4 hydrogens in that environment, 3 in that one and the 6 in that one, I get to 14. And just coming back to my molecular formula, that's how many hydrogens are in this compound. So that would suggest that I've correctly identified the whole number integration values. What I've also then written here, and what I did next, was I worked out the splitting pattern. So this here is a quartet because it's split into 4 peaks. Then we have a singlet, then we have another singlet, and then this one here has been split into a triplet. So I've written that down, and then what I personally always like to do is work out how many adjacent / neighbouring hydrogens there have to be in order to create that splitting pattern. So the rule is it's the number of neighbouring hydrogens, n, plus 1, will give you the splitting pattern for that peak. So if I know that this is a singlet, it has to therefore be that the hydrogen in this environment is next to 0 others, because 0 neighbouring hydrogens plus 1 would give me a singlet. To give me a quartet, there has to be 3 neighbouring hydrogens to the ones in this environment in order for me to then do 3 plus 1 and get to 4, which is my quartet. For the other singlet, again, those hydrogens need to be adjacent or neighbouring to no hydrogens, because 0 plus 1 gives me a singlet. And then for the triplet, the hydrogens in this environment need to be next to 2 hydrogens, or adjacent, neighbouring to 2 hydrogens, because 2 plus 1 gives me 3, which would make these hydrogens be split into a triplet. So we need to be really clear that the integration values, the 1, the 4, the 3 and the 6, tell me how many hydrogens are in each of those environments. The splitting pattern tells me how many hydrogens are in a neighbouring environment. Now you might think that these 2 peaks in particular are a bit weird, because we've got to have 4 hydrogens in one environment, which in itself is a difficult thing to do, because remember, if hydrogens are in the same environment, they're bonded to the exact same set of other atoms, and I'm not sure how we would get 4 hydrogens in the same environment. The thing that I can suggest for the CH3s over here, or rather the 6 hydrogens over here, is that there are 2 CH3 groups where all 6 of those hydrogens would then be in the same environment, but I'm not sure how I can do that for 4. So that might suggest that rather than having 2 CH3s to put all 6 hydrogens in the same environment, that there is a plane of symmetry in this molecule. Now that conclusion that I was thinking about as I was writing this information down became more concrete when I then looked at the chemical shift values. So if you were given this in a table, you'd probably be given an exact value for the chemical shift for each peak, but you can just look on the x-axis and have a look at roughly where they are, because all of the chemical shift data on the datasheet in table B is given as a range anyway. So I just had a look at this peak here, and it was about at 0.9-ish, and then I had a look over on my data sheet and I found that at 0.9 it was probably going to be the RCH3, which would make sense. If I have 6 hydrogens in the environment, I could have 2 CH3, where all 6 hydrogens could be in the same environment, but when I have a look at the quartet, which is found at around 1.4, 1.5, and I have a look for that chemical shift value on my data sheet, 1.4 to 1.5-ish would suggest either a single hydrogen on a carbon with 3 R groups, or perhaps more likely this one here, the R2CH2, which is what I wrote it down as here. Now, if I have 4 hydrogens that I need to be in this environment, and I'm saying that it's found at a shift value which suggests a CH2, I can't put 4 hydrogens into a CH2, but I can put 4 hydrogens into 2 CH2s, which can still then be in the same environment if the molecule is symmetrical. So that would suggest that we have a CH2 and a CH3 on either side of the middle of our molecule. And when I start putting this all together, you will hopefully see what I mean. For the singlet peak, found here at about 1.1, that also suggested an RCH3. And 3 hydrogens in that environment would suggest that they are all in the CH3 group, and then they just need to be adjacent to 0 others. So if we put that in the middle of our chain, we don't want there to be a hydrogen on that same carbon. And then the final singlet peak, difficult to identify the hydrogen of an OH group because, as you can see on the data sheet, it can range anywhere from 0.5 to 5 parts per million. But my clue for this is if you've got 1 hydrogen in the environment and it's a singlet and thus needs to be next to no others, that would be an indication, if you know from some other piece of information like we've got here, that there is an OH alcohol functional group present. 1 hydrogen in the environment represented by a singlet peak, that would normally suggest that that is the hydrogen of the OH group. So that's all the data I've annotated, and now I'm going to put it all together into a structure for compound R, and then I'm going to come back and explain from my structure how that links into all the points that I've made in this question. So here is the structure that I have come up with for compound R. Now, with NMR, I could sit and stare at everything I've written on this piece of paper for a long time, trying to visualize what this compound might look like. What I actually did was, once I'd come to the conclusion about the symmetry and I'd annotated everything around figure 2, I got a scrap piece of paper and a pencil, and I just postulated that this could potentially be the structure. And that would always be my advice on an NMR question. You have to get stuck in and just try and piece the different fragments together. Check then, once you've put the structure together, if it works, because you'll be able to see where it doesn't, and then you'll know which changes to make. But if you try and just visualize it all in your head to get the structure of the compound perfect first time, you're far less likely, in my opinion and my experience, to succeed. So I just scribbled down, oh, could this work as a potential structure? Then I did all of the checks that I'm about to do with you now. So the easiest thing to check first and foremost is that the structure I have suggested for compound R matches the molecular formula C6H14O. I've definitely drawn 6 carbons. I've definitely drawn 1 oxygen, and I'm just going to count my hydrogens: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that's the first thing checked. Going back to figure 1, we said it has to have an OH alcohol functional group. There it is. So again, that matches up with the infrared information. Obviously, by far and away, the hardest thing to check is the NMR information that we have. Now, focusing on each of the hydrogen environments by colour, starting with the green, there is 1 hydrogen in that environment, which I've drawn, and that would generate a singlet peak because that hydrogen, is next to 0 others. Now, because this hydrogen isn't on a carbon, we can't then consider what hydrogens are on neighbouring carbons because this isn't on a carbon in the first place. But even if that was how it worked, this carbon has no hydrogens on it. So I'm quite happy that that would give me my singlet peak. Going on to the red environment, which looking at the chemical shift was going to be a CH3 with 3 hydrogens in it, which made sense. And then we needed that also to be a singlet, so adjacent to 0 hydrogens. So immediately when I came to that conclusion, I knew that CH3 needed to be on a carbon that didn't then have a hydrogen opposite it. That's why I put the OH opposite this methyl group, this CH3, because I knew that that would then mean the carbon I've drawn in black, if I put carbons either side here, would have no hydrogens on it. And then that would give me this as a singlet peak, which is what I need. Had I put that not on the same carbon as the OH, then there would have been a hydrogen on the carbon opposite the CH3, and then that would have caused that to be split into a doublet rather than it being a singlet. That also would have given me issues with the number of carbons I had though, and the symmetry, if I tried to put the CH3 in red and the OH in green on different carbons. So that was another reason why this has to be the structure. And then going back to my purple and my orange environments, I have 4 hydrogens in total in the purple environment, but the chemical shift value suggested that they were CH2 groups. And then for the orange environment, we needed a triplet splitting pattern, and those 6 hydrogens were looking like they were going to be CH3s. So using that information, I've come up with this, where the plane of symmetry is obviously down the middle here, and then I've got the CH2 and the CH2 in the purple environment either side, and then I've got the CH3 and the CH3 from the orange hydrogen environment next to that. So the purple hydrogens, being adjacent to 3 others, would be split into a quartet. There's no neighbouring hydrogens on this black carbon, so we only need to consider the 3 in the orange environment. 3 plus 1 is 4, so those purple hydrogens would be split into a quartet. And the exact same thing is going to happen on the other side of the molecule. Those 2 purple hydrogens are adjacent to the 3 hydrogens in the orange environment. 3 plus 1 is 4, which would split this into a quartet. Now, when we're dealing with symmetry, it makes this process more difficult. But the thing that I spotted was having 4 hydrogens in the same environment. I don't know how you would do that when carbon can only form a total of 4 bonds and have everything else that we have here. For the orange hydrogens, we need those to be triplets, and those 3 orange hydrogens are next to the 2 purple ones. 2 plus 1 is 3, so they would indeed be split into a triplet, and again the same thing is happening on the other side. So those 3 orange hydrogens and those 3 orange hydrogens are in the same environment, totaling 6. That is a really tricky question. And when it comes to explaining your deductions for how you've put together compound R, you're going to have to be using the information that you've annotated onto figure 2. But that will make things lots easier because you've already annotated it onto figure 2. And all you will be doing is explaining how these different environments create these 4 peaks here with the splitting patterns that we observe, the integration ratio values that we have turned into whole numbers, and yeah, what the chemical shift on the x-axis tells you. Putting that all together gives me that as my structure, and that would be the answer for this question. NMR is tricky, and I appreciate that some of you may have questions about this specific question within this video. If you do, please reach out. You can comment on this video, or you can reach me via email, which you can get to through my website, missgtutoringandresources.com, or you can contact me on Facebook or Instagram or TikTok, although that's probably not the best way if you've got a question about this specific question. If you have any questions about NMR or would like some help with NMR, again, please do reach out and I will do my very best to help you. Again, you can reach me via any of those means, any of my social media platforms, or through email. Thanks for watching, guys. Hope you found it useful. Take care.